back to the course of applied elasticity. In this lecture, we are going to discuss about the balance laws. In last 3 lectures, we were talking about the different stress measures, and now from the stress measure we are going for the different balance laws. Now this balance laws includes the mass balance, linear momentum balance, angular momentum balance as well as energy balance. Now the first thing with which we are going to start is the transport theorem, and using this all these different balance laws can be derived. So transport theorem states that f x comma t being a continuous and differentiable scalar valued function for deformed position vector small x and time t. This is the statement of the transport theorem, where v is the velocity vector and n is the unit normal vector on the boundary surface capital gamma. So d dt, total time derivative of this f x comma t integrated over the total volume of the body. So we are considering a body defined by this v and the boundary surface is gamma. Now f x comma t is any property of the body which is a scalar valued function defined by the deformed position vector small x and time. So total time derivative of integral of f x comma t over the total deformed volume d small v is equals to summation of these two terms. First term is local time derivative del f del t integrated over volume plus the surface integral of f times v dot n, where v is the velocity vector, n is the unit normal vector to the surface gamma. So one term on the right hand side, the first term is volume integral, second term is surface integral. So first term takes care of the local changes within of the property f within the volume within the body, whereas the second term, convective term, that takes care of the changes due to property f due to change of the boundary surface, and in total summation of these two results the total time derivative of this property f x comma t within the body. Now moving forward, first we are going to talk about the mass balance. Let us define the density as a scalar field rho x comma t, which is defined as limit delta v tending to 0 delta m by delta v, where delta v is the volume of a small element whose mass is given by delta m. So density rho is limit delta v tending to 0 delta m by delta v. Now total mass of the body can be obtained by integrating this rho over the entire volume. Now if this volume integral is with respect to the deformed volume d small v, then we define that mass with respect to current configuration, and if this volume integral is with respect to the undeformed volume d capital V, then we define the mass as integral of rho naught capital X comma t d capital V integrated over the undeformed volume in the initial configuration. So this expression, if rho is function of small x and integral is over small dv, then it is current configuration definition of mass. If rho is function of capital X and integral is over d capital V undeformed volume, then this is the definition of mass in the initial configuration. Now for the principle of conservation of mass, this implies the total mass of the system remains constant at each and every configuration. Thus rate of change of this mass, total time derivative of this mass of the system must be equals to 0. M dot, here this dot refers to the time derivative, total time derivative d dt, where d is all capital, dm dt or m dot, rate of change of mass equals to 0, and we are going to write the expressions of all these balance laws in the current or the deformed configuration. So we are taking the definition of mass in the current configuration, and thus d dt total time derivative of integral rho x comma t d small v equals to 0. This is the mass balance in the current or Eulerian description. Now using the transport theorem, we are simplifying the left hand side of this equation d dt of integral rho d small v integrated over small v using the transport theorem, where f x comma t that scalar valued function is chosen as rho x comma t. So, if you look back at the transport theorem, replace f with rho. F can be any scalar valued function. For mass balance, we are choosing that function to be the density, rho as a function of small x and time. So, substituting that in the transformation in the transport theorem, we will be getting this d dt of rho integrated over dv equals to del rho del t integral over dv plus rho times v dot n, where v is the velocity vector, n is the unit normal on the surface, and this last term is integral over the surface d gamma. Now, using the divergence theorem for the last term, if we use the divergence theorem, we can convert this last term from surface integral to the volume integral, and that would be this term rho v dot n d gamma integral would be dv integral divergence of rho v. So, whatever is the coefficient of n, divergence of that would be added, and d gamma term would be changed to dv term. Surface integral will be changed to volume integral if you are invoking divergence theorem. Thus, the left hand side m dot becomes volume integral of del rho del t plus divergence of rho v, where capital V vector, this vector is the velocity. Do not get confused with the volume, undeformed volume. Undeformed volume we are not involving in this particular calculation, because all our description is in the Eulerian description. The volume is d small v, whereas capital V refers to the velocity field. Now, for d small v being an arbitrary quantity and this integral to be 0, we must have del rho del t plus divergence of rho b, the integrand which is there within the integration, that must be 0. So, in the initial notation we can write divergence of rho v as rho v I entire thing comma I. So, del rho del t rho v I comma I equals to 0. This is the mass balance expression in the Eulerian description. Now, we can further simplify this. This comma I quantity can be expanded into two terms, once taking the derivative of rho, another one's taking the derivative of v I. So, two terms would be resulted, and it would be del rho del t plus rho comma I v I plus rho times v I comma I. Now, combining these two terms and using the definition of the material time derivative of rho in the Eulerian description, d rho dt is del rho del t plus rho comma I v I. So, first two terms in total results this d dt of rho, total time derivative of rho or density of the material, and next term is rho times v I comma I. v I comma I is divergence of v. So, second term is rho times divergence of v. So, mass balance can also written in this alternate form as d rho dt plus rho times divergence of v, and if the material is incompressible, rho is constant, d rho dt 0, for such cases the mass balance equation becomes divergence of v equals to 0. So, for incompressible material, divergence v equals to 0 is the mass balance equation. Now, moving forward to the linear momentum balance. So, let us consider a body, and within the body we are taking a small volume element dv bounded by small surface d gamma. Now, n being the unit outward surface normal vector on this surface d gamma, and T being the surface traction force acting on this boundary gamma, B being the uniformly distributed body force defined per unit volume, and V capital V being the velocity vector. We can write the linear momentum of the body as mass times velocity integrated over the entire mass. So, V is the velocity integrated over the entire mass. This defines the linear momentum of the body, and writing dm integral as d rho times dv integral in the Eulerian or the deformed configuration, the linear momentum would be integral rho in times velocity integral over the total deformed volume d small v. Now, principle of conservation of linear momentum states that the rate of change of linear momentum, that is this particular quantity, is equals to the net force, resultant external force acting on the body, and it can be mathematically written as d dt, rate of change of linear momentum. So, this integral rho times velocity d small v integrated over small v deformed volume, this is rate of change of linear momentum, that is equals to net work done. So, there are two terms, one is integral T d gamma surface integral, another is B dV volume integral. So, this first term T d gamma, that is the integral or total work done by the surface traction forces acting on the boundary surface gamma, whereas the second term integral B dV, this integral is the total work done by the body forces which is spanned over the entire material volume. So, these are the two work done, two external forces are acting on the system. On the surface T is acting, within the body B is acting, body force is acting, work done by both of them, both the forces are included here, total surface traction and total body force are added. So, as the rate of change of linear momentum, this left hand side is defined to be the net external force acting on the body, that is the surface traction integral, surface integral d gamma times T and volume integral B times dV. Now, using the Reynolds transport theorem with f x comma t being rho times v. So, here the scalar valued function f is chosen as rho times velocity, and substituting that in the transport theorem, left hand side becomes del del t of rho v dv plus rho times v multiplied with v dot n integral over surface. So, these are the two terms coming due by using the transport theorem on the left hand side of the equation with f x t replaced with rho times velocity or rho times v, and right hand sides remain same. Now, T I have written as sigma times n by using the definition of the Cauchy stress tensor integrated over d gamma, and last term on the right hand side is B integrated over dV. Now, considering the material to be incompressible and also using the divergence theorem. So, there are two surface integrals, this term, the second term of left hand side and first term of right hand side, both of them are surface integral. These are required to be converted into the volume integral with the help of divergence theorem, and considering the material to be incompressible, this rho we can take out. Del del t of rho v we can write as rho times del v del t, rho is not changing with time. So, doing this, assuming material incompressibility and using divergence theorem, this equation would be reduced to this particular form. So, if you use the divergence theorem for this particular term, this would be volume integral of rho v times divergence of v dV, whereas this particular term would be integral of v divergence of sigma dV. So, with this, if you are substituting both of them in the final equation and then use the definition of this material total time derivative dV dt as del v del t plus v times divergence of v. So, v times divergence of v terms come from this, and this del v del t term is already there in the first term. Combining both of them, the left hand side is having a single term rho times total time derivative of v, rho dV dt integrated over deformed volume is equals to divergence of v plus divergence of sigma plus b integrated over the total deformed volume. So, this is the linear momentum conservation expression. Now, simplifying that further, we can define a small a to be the acceleration vector which is total time derivative of capital V, that is velocity vector. So, in the first term this dV dt is written as a. So, rho dV dt is rho a, rho times acceleration minus divergence of sigma minus b integrated over total volume is 0. Now, as this integral dV, elementary volume dV is quite arbitrary, to have this integral to be 0 always, we must have the total integrand rho a minus divergence of sigma minus b to be 0. So, rho a divergence of sigma plus b equals to rho a minus divergence of sigma minus b equals to 0, which implies rho a equals to divergence of sigma plus b. In the initial notation, rho a I is equals to sigma I j comma j plus b I. This is the linear momentum balance in the Eulerian description, and this is valid both for static as well as dynamic problem, because we are considering the acceleration component a I in this particular linear momentum balance. Now, if we are just considering the static problem, V, the velocity field is 0, thus acceleration field is 0, the left hand side of this equation would go to 0. Thus, it would be divergence of sigma plus b equals to 0. This is called the static equilibrium equation, one very important equation which we will be using multiple times within this course. So, for solid mechanics problem, elasticity problem, as we are not considering the dynamics of the system, divergence of sigma plus b equals to 0 gives us the static equilibrium equation. In the initial notation, it would be sigma I j comma j plus b I equals to 0, where I varies from 1, 2 and 3. I is the free index, so we can have 3 static equilibrium equation along x1, x2 and x3 direction. So, linear momentum balance is basically giving us the static equilibrium equation for the strength of material or elasticity problems. So, after the linear momentum balance, now we are going to discuss about the angular momentum balance law. So, let us consider the same body where we are considering origin here for this x1, x2, x3 axis, and body force B per unit volume is considered acting over the small volume dV, and the surface traction T is acting over the surface d gamma, with n being the unit normal on the surface. So, the principle of angular momentum balance states that the rate of change of angular momentum of the continuum about a fixed point, that is origin O for this case, is equals to the net moment of all the forces acting on the body about that same fixed point origin. So, if you are calculating the angular momentum of the body about point O, rate of change of that angular momentum is equals to the net moment created by all the forces acting on the body about that same origin. Now, the two types of forces are acting on the body, one is body force, another is surface traction force. So, the moment created by the body forces and moment created by the surface traction forces, their summation is equals to the rate of change of angular momentum of the body. Considering x to be the small x to be the position vector of any point within the body in the deformed configuration, the mathematical statement for this angular momentum balance principle can be written like this. So, left hand side of this equation is the rate of change of angular momentum. So, this v vector is the velocity, and this rho v integrated over the volume dV is the linear momentum. Now, as we are taking the angular momentum here, that is written as the moment of linear momentum. So, if you are taking the moment of linear momentum about point O, that would be x cross rho into v, velocity integrated over the volume dV. So, this total thing is actually angular momentum of the body, and total time derivative of that d dt of volume integral x cross rho velocity is nothing but the rate of change of angular momentum. Now, this should be equals to the moment of all the forces. So, first term on the right hand side is moment of surface traction x cross t acting over d gamma integrated over the entire surface gamma, plus the second term is the moment caused by the body forces B, which is x cross B acting over dV and integrated over the entire volume of the material. So, rate of change of angular momentum d dt of volume integral x cross rho v is equals to surface integral x cross t, that is the moment of the surface traction, plus volume integral x cross b, which is the moment of the body forces. Now, writing this equation in terms of the initial notation, x cross rho v I am writing in using the permutation symbol as E I j k rho x j v k, then volume integral of that and d dt, rate of change of this quantity on the left hand side. Similarly, this x cross t can be written as E I j k x j t k, b x cross b can be written as E I j k x j b k. All these cross products are written with the help of permutation symbol. Now, considering the material to be incompressible, this rho is a constant. So, we can take that rho out of this d dt or time differentiation. E, the permutation symbol, is also constant. So, the left hand side term we can write as rho E I j k, then d dt of x j v k integral over volume minus second and third term are the terms coming from right hand side to left hand side, and thus we are having a change in sign. So, T k, this T k, the surface traction component, we can write in terms of Cauchy stress resultant as T k equals to sigma transpose k L n L, and using the symmetry or removing this transpose, we can write sigma transpose k L as sigma L k times n L, where n L are the components of the unit vector. So, hence the second term becomes minus the surface integral E I j k x j sigma L k n L d gamma, and finally the last term remains as it is, that is the body force term, moment due to body force minus volume integral E I j k x j b k integrated over volume. Now, moving further, the first term we can rewrite in this fashion. This d dt, the time derivative, is first acting over x j and then acting over v k. If x j we are treating as constant, the first term is x j times d v k dt, and then if you are keeping v k constant, so this would be v k times d x j dt. Now, x j being position vector, d dt of x j is nothing but v j, the velocity in j. So, the second term would be v j v k. So, d dt of x j v k is having two terms, x j times d v k dt plus v j v k in the first integral term. Now, the second integral term, which was a surface integral, that is now converted into volume integral using that Gauss divergence theorem like this. So, surface integral E I j k x j sigma L k n L is now written as E I j k x j sigma L k, this entire thing comma L integrated over volume, and last term remains as it is. Now, these can be simplified further like this. So, consider this particular term epsilon E I j k multiplied with V j V k. This is nothing but the cross product of the same vector V, V cross V. So, cross product of the same vector V is simply 0, and thus this term is not going to have any contribution. So, first term we are having as it is, that is E I j k x j rho d v k dt. Then coming to this term x j sigma L k comma L, these can be expanded into two terms. Once we are taking this partial derivative with respect to x L for the first term x j, another ones for the second term sigma L k, keeping another term constant. So, one term would be x j is constant, then sigma L k comma L. Another term is sigma L k is constant, and we are having del x j del x L. Now, this term del xj del xl is nothing but delta JL. So, this is the Kroneker's delta. Now, using the property of the Kronecker delta, we can write delta JL sigma Lk as sigma Jk. So, this particular term xj sigma Lk comma L is replaced with this, and hence combining all the terms which are having one xj common and clubbing them together, we are having these three terms. So, xj times rho d Vk dt minus sigma Lk comma L minus Bk, this minus sigma Jk, then entire thing multiplied with permutation symbol Eijk volume integral over dV equals to 0. Now, once again starting from this and writing dVk dt as Ak, the acceleration component, the first term would become epsilon Eijk xj times rho Ak minus sigma Kl comma L minus Bk. This entire thing is multiplied with xj. After that, we have minus sigma Jk integral over dV equals to 0. Now, if you recall the linear momentum balance, what was that? Linear momentum balance was rho Ak is equals to sigma Kl comma L plus Bk. So, that was nothing but rho A vector is equals to divergence of sigma tensor plus B vector. This was the linear momentum balance. In the initial notation, if you express that, that would be resulting this particular term, and thus this entire term goes to 0, and hence we are only left with a single term for the angular momentum balance, that is dV integral deformed volume integral of Eijk sigma Jk equals to 0. Now, dV being a small arbitrary volume element, for this volume integral to be 0, we must have Eijk sigma Jk to be 0. So, Eijk sigma Jk to be 0. Now, if we are having this element to be 0, we can write that this element is same as minus of that element. So, if you are able to write A equals to minus A, that implies A equals to 0, because 2A is 0 and then A should be 0. So, same thing we are trying to write here. So, Eijk sigma Jk is equals to minus of Eijk sigma Jk. Now, slightly manipulating this term with the indices, by changing the indices, first I am flipping I and j. J is replaced, no sorry, I am flipping k and j. J is replaced with k and k is replaced with j. Interchanging these two indices, this becomes minus Eikj sigma kj, and then this minus of Eikj can be written as plus of Eijk. This is equals to minus of Eikj. Thus, this quantity, the initial quantity Eijk sigma Jk is shown to be equals to Eijk sigma kj. Now, Eijk being common, we can cancel that Eijk, and thus we will have sigma Jk equals to sigma kj, means sigma is equals to sigma transpose. The Cauchy stress tensor is symmetric. So, from the angular momentum balance equation, we are once again coming back to the symmetry of the Cauchy stress tensor. So, angular momentum balance equation ensures the symmetry of the Cauchy stress tensor in the deformed coordinate. We are writing all these balance equations in the deformed coordinate, and as Cauchy stress tensor is the deformed stress measure, we are getting the symmetry of the Cauchy stress tensor by the angular momentum balance equation in the deformed coordinate. So, in this lecture we had first introduced the transport theorem, and with the help of that in the deformed coordinate we had derived the expression of mass balance, then linear momentum balance, which basically results the static equilibrium equation for the static problem, and then finally angular momentum balance resulting the equality of the cross shear of the Cauchy stress components. Thank you.